Please, our next speaker is Maciek. He's an Algrebraic topologist turned software engineer with over 18 years of experience. He's building systems on JVM and Rust. In his talk, Maciek will explore what really happens to your code after deployment. He'll reveal how compilers, JITs, and hardware optimization can transform your code in unexpected ways.
Yeah,
Please give a warm welcome to Maciek.
Sorry. Yeah, so welcome. Welcome. I'm really glad to be here. Welcome you all, and hope you're enjoying the conference. So I'm Maciek, and this is, I don't remember which time at Heapcon it is, but yeah, I've been here for many times. So I'm still happy to be here. And as it's been said, right, for many years I've been working on JVM and a company called Toke, and I've been doing it for like 14 years, and still it took this year's organizers a few months to really understand that I'm no longer Toke. I'm at a different company, so yeah, at the previous versions of the speakers list, I was still at Toke, and then I was working on Scala, JVM, and interesting stuff like that. But now I'm working at some different place. It's called Hyperexponential, and it's more stuff with insurance, let's say, and I'm working on a totally different technology stack that is mostly Rust, Python, and stuff like that. So a big change because, you know, I had this midlife crisis, had to change something. And this change is also kind of like an inspiration for this talk, right? Because for many, many years I've been doing JVM development, and, you know, life was simple. When I had a string, I just created it, then I created some more, added it, and you know, the mighty JVM figured out what to do next, whether to allocate some memory, whether not. Does it use a string builder or not? We don't care. We care about it only during the JVM interviews, right? But now, when I'm working in kind of like a bit low-level languages, now it's my decision whether I need to allocate the memory, whether I need to clone it, whether I need to, you know, change it. Life is becoming more and more difficult, so I started to figure out what's really inside, and also got me thinking, do I really understand after these 14 years how the JVM really works? So this is kind of like inspiration of this talk, because, you know, at some point this is our simple mental model of how stuff works, right? We have memory, we have CPU, and yeah, that's all. If we think a little bit deeper, maybe we know that, okay, there is some stack, there is some heap, things are moving around, we invoke some instructions, they get executed, and so on. But in reality, this is how stuff works, right? It's not even the newest Intel CPU, but this is kind of like, I think, from like 5 or 10 years ago. I think this is the hassle. So you can see, where is the memory heap? Where is the CPU? I don't know, right? So let's look just a little bit inside. And before we look into CPU, let's start a bit with the compilation, right? Because this is the first part where the rows of my current workings on Rust, which is kind of like lower level language, and JVM start to diverge, right? Because in Rust, first you start with the code, and then the mighty compiler generates some LLVM intermediate representation, which is a great example of external DSL, right? Which this is the compilation target, and is totally unreadable for a human being. And then the optimizer kicks in and generates some real machine code that is ready to be used by the computer. And everything happens during the compilation phase, which is why it's so freaking long. And in JVM, things are a bit different, right? First, we have something called compilation, but it doesn't do anything interesting. It just turns code to the bytecode. But as we all know, it's kind of like still quite similar to the original sources. But the interesting thing kicks in during the execution of the Java code, right? And then we have the mighty hotspot compiler, which has a lot of phases, tired compilations, C1, C2. First, it generates the machine code. Then, after many cycles, another layer of compilation called C2 might kick in and produce optimized code. And if it turns out that it's really incorrect because we download some arbitrary code from the internet and recompile and stuff like that during the execution, then we go back to the bytecode and start all over again. So this process is a bit more complex, and also it happens during the runtime. So the interesting question is, can we really look inside, right? Because with the static statically compiled languages like Rust, we can, take the resulting SO file or something like that and peek into it. But what about JVM? Yeah, and coming back to Rust, before we come back to Rust, let's look at this mighty list of various optimizations that can be performed by compiler, either during the ahead-of-time compilation, as is in Rust, or in just-in-time compilation, as it happens in Java. And for the Rust, or similar languages, you can also do it for C or C++, we can have quite a nice tools that allow us to peek inside the generated code. This is a program that I learned about not so long ago from my Rust colleagues. It's called Godbolt or Compiler Explorer, where you can give him source code, and it will show you resulting assembly after all the compilation phases. I'm sure you don't see too much, but it's OK, right? The most interesting thing is that you can take this assembly code and map it actually to the source code and see how it goes. This is how I learned that modern assembly has so freaking many instructions more than what I learned at the university. And also, it can give you quite a lot of hints what the code actually does. So still, here you can feel slightly bit safer because at least you can peek inside. But what about JVM, right? We don't know what really will happen when we invoke the code and it runs for like minutes, hours, or whatever, right? And here it turns out that, of course, we can pass a few more parameters to our JVM invocation that will collect various statistics that will enable us to print information about just-in-time compilation and generate a nice compilation log. And because we are in Java, what format does it have? Of course, it's mighty XML, right? So you get a, I don't know, few hundred megabytes log of compilation phases in XML, and you can have a look what's inside. I'm sure you can see what it does, but yeah, let's try some better tools. And it turns out that such tools exist. One of them is called JIT. It's not so new and slicky. You can, of course, see that it's been written in Swing, because you all can see it. And it takes this log analysis, and it can print you where exactly the just-in-time compilation happened, right? You can see where the code was generated, how much of this was generated, and we can also look a little bit more inside. It can, again, you can see it swings, so like, we can see what really happened with our code, right? So here we can see which parts were actually compiled to the machine code, and also which parts were inlined. Inlining is one of the base optimization techniques of the just-in-time compiler. So we can see that, for example, here at this C1 level, this is the first level of optimization. We don't have too much inlining, but after iterating more and more times, far more things were inlined, and our code might look very, very different, because inlining can be cascading and also be connected with other optimization techniques. So here you can see that the code looks much different, and we are at this last level of just-in-time compilation. So this is the first lesson, like that all those techniques, inlining and so on, might make our code look very, very differently to what we would expect. And it can be really barely recognizable. Let's look a little bit deeper. This is one of the, basic things that you can do in OOP languages, and that is create an interface and create two implementations, right? We have two implementations of this method called dispatch. One is returning 1, the other one is returning 2. And how the runtime actually decides which method should be called, right, after all the compilation? Well, in Java, it looks more or less like this. First, we have some object. Then, when we have the object, which we know implements this dispatch interface, then the runtime looks up the actual method that it should invoke in some vtable, and then it knows it should go to this implementation of that. This is kind of like a function pointer. And the common knowledge among at least maybe, how to say, performance-savvy Java developers is that this whole stuff well, it's not too performant, right? Because you have to perform this lookup, go to another place in your code, and so on and so forth. So let's have a quick look, right? Here in this case we have a table of these dispatch values, right? And some of them are this D1, D2, D3, right? And we iterate, right? And here the runtime needs to take the decision whether to invoke D1, D2, or D3. And if we go to some profiling tools, I won't even get into the details which one is it, but no worries. We can see that somewhere in this call stack, quite a lot of time is actually being spent in this place called vtable chunks and so on. So this is where we confirm our speculation that, yeah, this part might be not so optimal in terms of performance. But, and we also can see it on the JIT, right, where we have this special color purple called virtual call, and we see that that the runtime indeed goes to all those gory details. But what will happen? This can be kind of like a little bit surprising when we only have two of them, right? We have only D1 and D2. We stripped out the D3. What happens? And we run the code and look at the JIT watch, and surprisingly, now it could actually inline our calls, right? So somehow, there is some threshold in this JIT compiler when it understands that, okay, this should be a virtual call, but in the end, I'm deciding that, no, there are just two cases. I'll generate some static ifs, I would say, and we'll be able to inline the calls. And lo and behold, if we run our performance test again, we can see that, okay, there is something, but no mention of these vtable chunks. So indeed, this simple change, which we wouldn't expect to change that much, really caused the compiler to kick in, perform different optimizations, yeah, and things change quite a bit, which might, again, affect the performance. So this is interesting because, in fact, in this sense, the compiler does something similar to what Rust compiler does during the ahead-of-time compilation, right? Because in Rust we can use the technique called monomorphization. It's not always applicable, but in many cases you want to be able to use it, where during the compilation time, the compiler, by analyzing the code and various generic invocation, can decide which of those methods it will invoke, right? So this is done during the compilation time, so we cannot rely on runtime data. So this technique is kind of like a bit more difficult to follow, but it works very well when it can be applied. And it was kind of like a surprise for me that the mighty JVM compiler can also detect some of those things during runtime and, well, applied those kind of like monomorphization, a little bit techniques when the code is running to make it faster, right? And I mean, as a developer, don't need to do anything. So for me, this is another kind of like example of tour de force of JIT and how good it can be. And let's look at yet another one. This time, this will be a bit more in the spirit of Ts. I don't know if he's here. He likes functional programming, so let's do a little bit functional programming here. And the tenet of functional programming is, of course, we don't modify object, we create new, the modified one. So we have a simple container which has x, y, and when we want to add something, we don't mutate our container, but we create a new one. And we create a new one. Let's do it for like thousands and thousands of times, right? So each time we create a new container, new object, we add, something is going on. Let's not to think too deeply if it makes sense, but we can see that we create a lot of objects, and this is mostly how functional programming in Java look like, right? We create new and new and new. Of course, they are very, very short-lived, so we expect that the garbage collector will clean them out pretty soon because, hey, in this loop, I'm creating here a new one, here a new one. But when I return from this loop or from this method, right, they should be gone. But we expect that they will be created, so it will affect performance somehow, because even if creating new objects in Java is pretty fast, there still should be some pressure on the GC. But when we run a benchmark containing this stuff, we can see that actually, this is again some standard Java benchmarking tool. We can see that actually there's no garbage collection. And if we look here at the thing called GC allocation rate, we can see that it's kind of like negligible, right? That we almost don't allocate anything. So again, we start to think, what the hell is going on, and why the new objects are not created? Is it something connected to the fact that we cannot monitor it because it happens so fast? But in reality, something different happens. Again, this is kind of like not so easy to read out because this is JIT watch, but you can see that, okay, there are some mappings of this method to the ASM code, and some of them don't read them because, yeah, this is not so needed, but you can see that some of them are actually crossed out. And if we look at some of the hints from the JIT watch, you can see that actually it says, hey, heap allocation of what was eliminated due to inlining. So what it means is actually at some point the JIT compiler started to think, and perform something called escape analysis. So it understood that all the objects that we created actually don't even survive the method code, right? They don't escape from the method. So then it thought a little bit more and concluded that, okay, hey, I don't even need to allocate them on the heap, right? Because this is still something that takes a few more CPU cycles. I won't allocate those container instances of the heap, but I will just leave them on stack. So this is a little bit more involved optimization, but as you can see, it can lead to pretty good results, because here we have the first example, right, with no GC allocations. And let's say what will happen if we turn this optimization on. You can do it for all the, or at least most of the optimizations that JIT performs. And here we can see that, indeed, if we don't do this escape analysis thing, you can see that there were like 200 GC garbage collections. The allocation rate was quite higher, but most importantly, also the performance is much worse, right? Here you can see it's like 700 something nanoseconds per operation, and here you can see it's like 3,700 nanoseconds, right? So again, this was kind of like pretty interesting for me, that the just-in-time compiler could conclude that it doesn't need to allocate stuff on heap. And this, again, brings me to my Rust experience, because there, if I have a struct, which is kind of like a little bit like class in Java, that's called container, and I can do plus, then in fact this thing won't be necessarily allocated on heap, but on stack. Why it's possible? It's more connected to how Rust does its things and how does it actually manage the memory. Let's not get too deep into that. But if you go to the documentation, it says that, okay, values in Rust are stack allocated by default, which is very much unlike in Java. If you want to allocate them on heap, well, we can do it using special techniques. And Java is the other way around, right? First, everything is allocated on heap, more or less, let's say it like that. And it turns out that, again, the JIT can think for us and optimize the whole thing and move it to stack. I think it's some of the newer languages like Go, there's also this notion of detecting whether the stuff can be allocated on heap or stack, and this can also lead to better results. And even more interestingly, the Java is still evolving, and there's the ongoing project Valhalla, which I think it's JVM preview for like many, many years, so there are a lot of technical challenges there. But the idea is to be able to declare a Java class, like so-called value class, and of course it will have some limitations, but by default, this thing will be allocated on stack on heap and not on the heap, right? Which can lead to very interesting properties anyway. But this is the future for the Java, and right now the interesting, at least for me, observation was that this JIT compiler can really affect what and how objects are actually created on the heap, which again can have quite a high impact on our code. So this was for the compilation. We don't have that much time, so let's go a little bit deeper on the computation side, right? So we have our code generated, the machine code generated either via static compilation like in Rust or at some point of execution in JIT. And let's see what's going on, right? Because as we all know, the CPU and the cores are still a bit more complex when we think. We have many cores, we have caches, stuff like that, the memory. Let's see if we can see the effects of this architecture on our programs, and if anything if we can see that changes in our code will be affected by this architecture. And this is yet another kind of like a bit more interesting example. So we have a stupid loop. We have an array somewhere. We iterate over it, and we increase the counter. Basically, we sum stuff in the array. And here, we iterate through all the values in the array. And here, we take only the 1/10, right? So each tenth of the element is taken. So naturally, you would think, right, that this should perform more or less like 10 times faster, right? We take only 1/10 of the stuff. But if you go again to some benchmark values, you can see that, in fact, this calculating of all the stuff is almost like only 2 times slower. So again, this is kind of like surprising. And why is that? And here we need to go a bit deeper and look at the architecture of the model CPU, right? Where we have the processor, we have the memory, but as we know, the memory is far away from the processor, so taking the values out of the memory can be quite expensive. So that's why the modern CPU have various layers of caches, and lightly used values can be taken from there. But what is also important is that when the CPU says that, okay, I need to take this value from the memory to the cache, it doesn't take only one, I would say, byte, one number, but it takes a bunch of it, called like line or cache, line or page. So adjacent values are also taken to the cache. And this is more or less what is happening here, right? So when we sum all the elements to the array, we take much more elements on iterations to the cache, and on the next iteration of the loop, they are already in the cache, so it's kind of like faster. And how we can really observe it, and then there are quite a bunch of interesting performance measurement tools, which are kind of like more used in C or various kind of like system-level programming. One of the most well-known is perf, which is a powerful tool because it can use something called performance counters in the modern CPU. So there are various metrics that are implemented in the CPU itself, and all we need to do is get the values out of there. And it turns out that it works also quite nicely with Java programs, also for profiling. But here, let's see what those performance counters, this time cache references and cache misses, will tell us. And this is what they are saying. When we take all the values, we have like 700 cache misses per operation. And when we iterate only over 1/10 of the values, we can see that the number of cache misses is much higher. And this is more or less the cause of this strange performance behavior. So for me, this is kind of like also pretty reassuring that even using our kind of like high-level language like Java, we can also observe those kind of like lower details of the CPU architecture, which might be not so, at least I don't know. For me, it was not so obvious for quite a long time that I can actually measure this thing. And let's look at yet another example of those phenomena. This one, again, we have a long list of integers. Let's not into the gory details of how do we actually create it. And then what we do. We take all the values, and for the first half of it, we subtract the values. For the next half of it, we increase, right? So there's the iteration, and here there's this large if. So this code works. And now let's make a small modification. Let's shuffle the list here, right? Because if we generate this array, it will be ordered, right? Because we take the in stream, it will take 1, 2, 3, and so on, right? And here we are shuffling, so this time it should have random order. So of course the result of the program is still the same, right? It doesn't matter. In which order we are performing those the inner part of the loop. But again, it turns out that in terms of performance, it's much different. And if we look at the randomized version, we can see that it performs much worse than the sorted one, because here we have like, well, less than 1 operation per millisecond, and here we have like 5. I don't know if it's 5 or 5,000, but it doesn't matter, right? So you can still you can see that the sorted version performs much better. And this is again a place where we think, okay, so this is our high-level language called Java. Why do we really see such effects? And it turns out that again, due to the fact that the JIT compiler can do various things, we can move quite closely to the bare metal and observe what CPU really does. And what modern CPU really does when it executes this sort of simple instruction, right? So we have a branch, right? We have if we either increase or decrease, simple as that, then what will our modern CPU will do? So it turns out that the execution of kind of like single instruction in modern CPU is much more complex, right? There are multiple stages of the execution. First, we get the code, then we prepare, then we execute, then we do something else. So there are various stages in this execution pipeline. And what really happens is that only, in theory, it should work that only after we know what was the result of this if, right? Then we know which next instruction shall we take and execute. But if we look at it, we can see that all the other stages of this pipeline are not doing anything here, right? Because we are waiting to know what will be the next instruction. So what the modern CPU does is actually it starts speculating, right? Because we all love gambling. I don't, but still. And it figures out that, for example, if the last 1,000 times we took this branch, then, hey, maybe next time it will be also this one. And what it does, it doesn't work for the result of this. It doesn't work for this result of this instruction, but it starts computing the result here as if we indeed took this branch. Of course, it's somewhere underneath. It's much more complex than that, but we can think about it this way, right? And when this instruction finishes, we already almost finished computing the next one. So far, so good if our bet was correct. And if it was not correct because, well, this time we took the different branch, well, so what? Then we just ditch the results of this computation and start all over again, right? So nothing happens, but we wasted quite a few cycles. And this is indeed what is happening for our shuffled list, right? Because if remember that we increased the counter for the first half of the list, so for, I don't know, few thousand invocations, right? We took the first branch, and afterwards we took the other one. But if we shuffle the list, then the order is random, and this branch prediction thing won't work. So it turns out that, again, there are some performance counters, at least on Linux. On my Mac, unfortunately, it's not so easy accessible, but yeah, on Linux, we're better to go. And there are performance counters like branches and branch misses. And here, the interesting thing is, again, we can see very closely that for the sorted version, the number of those branch misses is much lower than in the random case. And we can deduct after some thinking that, hey, maybe this is what affects our performance. So again, this is, if you think about it, this is pretty amazing, because here we're not even talking about JIT, right? We're not talking about JVM, right? This thing would happen also in Rust, which we would say that, okay, there's no just-in-time compilation. Everything is compiled down to machine instructions during the compilation phase. But now it turns out that it's almost like the modern CPUs has kind of JIT compiler inside. So things are kind of like much more complex than we might think they are. But we have to end, of course. But this is just the beginning, because so far we were talking only about stuff that, well, they can improve or worsen our performance, but we didn't take into the abyss of, are those things actually correct? Because in Java, we are mostly safe. The Java has good specification that tells us, OK, this is how our program will look like. This is how it will work. But in C, you have a long list of undefined behaviors. And if you do one of these sins pointed out here, it means that the compiler has kind of like license to kill. It can rearrange during the compilation of your code, whatever it works. So yeah, this is the dangerous territory. And also in kind of like similar, seemingly more safe conditions of Java, there is also the thing called multi-threading. And then we could spend probably another few hours talking about how compiler optimizations plus optimizations of the various types of architecture of the processor might mangle our code, and how many different unexpected results we might get. Because at some point, our multi-core processor is something like distributed database, and in our considerations how it really works, well, you need to apply various concepts of consistency that we can derive from the works of well, distributed databases and so on. But fortunately, I think fortunately we don't have time for that, and we don't have time to read the this is again part of the Java specification. If you start reading, well, yeah, it will take you some time. So we won't be doing that, and we will finish because I'll be pulled off this stage soon. So for me, one thing that I kind of like learned from that is JVM and similar stuff are really amazing, and the stuff that it can do and the stuff it can improve your code. This is truly amazing stuff. And also, even in high-level languages, we can observe lower-level details, which is also might not be so surprising, but it's still quite instructive to see it's working. And of course, the compiler can change code in a way that we don't even expect. And let's hope that it will remain correct. But if we go to the multi-core stuff, then we better use Haskell, right? I think that will be much better for us to do than JVM. And I'll leave it to you. I hope you enjoyed the rest of the conference. And yeah, of course, sorry, don't have time to questions, but yeah, if you want, we can chat anyway.
Thank you.